Okay, good morning, everyone. We're going well, he's going to defend, Saulo Javier Ronquillo is going to defend his PhD, his master thesis with this title, and you have about 30 minutes for the presentation. Then we'll have
Good morning, everyone, and welcome to the defense of my master thesis that was titled Opinion Dynamics in Social Networks Under Bias, a study based on the DeGroot model. In this presentation, I will introduce you the DeGroot model and how we can apply it to study bias in the society. And also we analyze how these bias affect the process of convergences of opinion. So I want to begin my presentation with this illustrative example. Let's consider a lottery winner. This person wants to invest in the oil sector, but he doesn't know anything about the oil sector. So he asked three people to make a prediction of what will be the price of the oil in a year in advance. So he asked two economists, a machine learning expert, and as his personal guru that advised him to keep buying lottery tickets. And actually, that's why he won the lottery. Each one of these persons, by his own methods, arrived to a value, a prediction value, a different prediction value. So now the lottery winner have to make a way to capture these different opinions in just one. So he made a decision that he will put these opinions in a way that reflects these preferences. So as the astrologer makes his prediction that makes him win the lottery, he gives twice the importance to his opinion than the other ones. So now, but in order to be able to capture these preference, we have to normalize these values. So at the end, the astrologer will have half of the importance, and the other people will have a quarter of the importance each one. So with this way to capture the opinions of all the three people, we arrive to a value of 155 euros. That's one way to combine the opinions of the people. Formally, this was explained by the group in 1974, where he explained that the way that the people in a society update his opinion is making upon the average of the opinion of the other people. He is bounded by the value of W. He doesn't mention how we can assign this W value, but he said that this must be non-negative and the values must add up to 1. It means that the attention that each individual have must be spread in his neighbors and must be equal to 1. In the matrix notation, we can express it like a W matrix where each element are these weighted with these weights and multiplied by the actual opinion give you the next time opinion. Now, for the characteristic of the W values, we have that this matrix W is a matrix, a stochastic matrix. Now, we can see that a more logical way to assign these bounds is not assign nothing to the opinion of the astrologer because it doesn't rely on well-documented methods. We don't know how he reached to this value, but we assign the importance, splitting it in half to the economists and half to the machine learning experts. So we can arrive at another value that maybe is more justified to take. But we now see that these weights are different ways to represent these weights. Here we say that one possible, these ways can represent how biased are the people for the other group, for instance. Now, let me introduce a society of birds. In this group, we have a group of hens and one group of roosters. We can say that there is an in-group bias if the individuals of one group put more attention or more importance to the characteristics or the opinions of the individuals of the same group, represented here by the hens. A real example of this was found in the hiring processes in a university hospital, where the candidates that were evaluated by personals that went to the same university that the candidates graded better this postulation than if we were graded by an independent jury. By the other hand, it's also possible that the individuals put more attention to the individuals in the other group. So now we are talking about the out-group bias. And a real example of this was found in a survey made to students of Manchester University that perceive that students in the Oxford University are more hardworking. In this study, this relates this with the people when compared with higher social level people tend to put more interest in that other group. So now we have seen that this bias affects the society. So that's why our main objective in this work is analyze how the in-groups and out-groups bias influence this consensus formation. When we talk about consensus, we are talking in the state where all the opinions in a society are the same for everyone. Also, we want to explore how the structure of the social network influence this process. And moreover, we want to know if it's possible to mitigate these effects of the biases, introducing more agents. Now, these agents will be neutral. When we're talking about neutral agents, we're talking about the people that don't show bias to the opinions of the others. And due to his neutrality, also, these people don't put bias in the opinion of the neutral agents. In order to do that, we're going to show you how we do it how we adapt the group model in the case of two groups, sorry. Here we can see the equation of the classical DeGroot model, but now we took these weights, and we introduced the bias parameter alpha, in the way that if the individual I is weighting the opinion of the individual J, he do in the assigning alpha over sigma I. And if they are in the same group, but if the individuals are from in different groups, he assign 1 minus alpha over sigma. Sorry. This value of sigma is a normalization constant that depends on the agent I and his neighbors. So we can calculate it as alpha times the neighbors of I that belongs to the same group, plus alpha plus 1 minus alpha times the number of the individuals that are neighbor of I, but doesn't belong to the same group. This is due in order to keep the restriction of the weights of the DeGroot model that the weight must add to 1. Here's an example of a society of bird when we assign the edges is the attention that our agents I, J, K, L put to the other agents, and the weights is put it as mentioned before. We have to mention that this bias parameter is defined between values of 0 and 1. And allow us to simulate different situations of bias in the society. Let's start explaining what happened in the strong cases when alpha is equal to 1. In these cases, we have a strong in-group bias. That means that the individuals only put attention or importance, give importance to opinions in the individuals in the same group, and doesn't listening to the ones that are belonging to the other groups. If we decrease this value, we're going to be in a region that show in-group bias until we reach the point of 0.5. In this point means that there will be no bias in the society, that in this context is that we weighted in the same way if the individual belongs to the same group or the other group. And if we keep decreasing, we're going to be in the region of our group bias until we reach the value of 0. That means that the individuals only listen the opinions to the individuals that don't belong to the same group. Now we want to see that this characterization can be described in this diagram where we have two groups and they are assigning an alpha value to the individuals in the same group and 1 minus alpha to individuals in the other group, and then we have to normalize it. But we also want to analyze the case when we introduce the neutral agents. Now, in this case, will be quite different. So now we part from the cases we have two groups, but we have a third one that is the neutral. In this case, as we saw before, the unnatural weight that this agent put is going to be 0.5. So that is represented in this diagram. And also, individuals for group A and group B weighted the opinions of the individuals of the neutral group with this unbiased value of 0.5. The way that we are characterizing the societies will be in three different ways. Using the complete networks, and we use Erdos-Renyi networks and Barabasi-Albert network. We want to use bidirected network. It means that when individual I is connected with individual J, also individual J is connected with individual I. Well, now it's important to recover some concepts to the related with the DeGroot model, to the classical DeGroot model. That is, what are the conditions to have consensus in this DeGroot model? There are two conditions. The first one is the network is strongly connected, and the second one is that the network must be aperiodic. So I will show you the explanation on this. First, the strongly connected network means a network that can be every pair of nodes in the network can be reached for a path, at least at one path. Here is an example of a very simple network that we can see that we can go towards any individuals for any path. So it's strongly connected. And now, what means that a network will be aperiodic? To say that a network is aperiodic, it means that a strongly connected network, the greatest common divisor of the simple cycle is equal to 1. So it's not so simple to see. So let me show you if this simple network is aperiodic or not. So we have to measure the simple cycles. First, a simple cycle is a path made of nodes that start from the same individual and end in the same individual. But the individuals that will be visited will be different. For example, we can go from I to J and then go back to I. There is a simple cycle. And also we can go to IL and then go back, and also with K. The length of the simple cycle is calculated as the number of individuals that were visited minus 1. So now we have that all have length of 2. Let's make the same thing, but now with this J agent. Now the simple cycle of this agent will be going to I and then go back with a length of 2, and there's no more simple cycle. Why? Because we can see that another path that the agent J can have is go J, I, then L, and go back to I, sorry, and then go back to J. That's a cycle. But it will be not simple since we pass through I twice. So it's not simple. So there is no any other simple cycle in this example. And it's clearly that due to the symmetric of this example, that also there is only one simple cycle for K and I. So in this case, all the simple cycle have length of 2, so the greatest common divisor is 2. That means that the network is periodic. So why is a simple way to get a periodic network? Let's suppose here we have a bidirectional network, so always we have cycle of length 2, that is going to J, I, and then go back. Always we have. But if we make that the network have a triangle that is simple cycle of length 3, where J, I, L, and J, then we're going to have simple cycle of length 3. Therefore, if we calculate the greatest common divisor, will be 1. So the network will be periodic. This is the case of the Erdos-Renyi network and the Barabasi-Albert, since they have non-zero probability of have triangles. Knowing that, we now to look at the results that we found in our analysis, starting for how are the opinions trajectory towards the consensus for different values of the bias, starting for the extreme values. It means that we have in this graph, we have the opinions of the two groups, the members of two groups that are equally of equal size. 10 individuals of group A with opinion 0 and 10 individuals of group B, with starting opinion 1. What we have seen that when we have this parameter bias is a strong in group bias. It is that the members of one group doesn't listen to the other groups. That makes that these initial opinions keep freezing in time and never change. Clearly, what we have here in order to don't have consensus is that the network is not strongly connected. We have seen here in this image the corresponding trajectories to the Erdos-Renyi network, but we have found the same behavior in complete networks and also in the Barabasi-Albert. Now he showed the result when we are in another extreme value of the bias, that is when alpha is equal to 0. Now the individuals only listen to the individuals in the other group. What we have found here is that these opinions are always oscillating between 1 and 0 in each iteration. Now, the condition that is not fulfilled here is that the network is aperiodic, because now there is not possible to have triangles because the trajectories will be one individual of my group then one individual of the other group, and will be in pairs. So the greatest common divisor will be 2 in this case. And then when we move towards how are the opinion trajectories when the society is no stronger biases, we have found 2 different behavior. One of these is when the society is in the region of the O group bias that is shown here in the left, and we have seen dumping oscillation. It is the opinions change over time, and then we reach the consensus. On the other hand, when we have a strong in-group bias, we have seen that this convergence is smoother. Smooth. In order to understand this behavior, we have to recall that the group model predicts that the opinions of the society at time t can be calculated as elevate this weight matrix to the power t and multiply it by the initial opinion. It's useful to make this representation in using the eigenvalues and eigenvectors of the matrix, the weighted matrix. And because this allows us to use a characteristic of the stochastic matrix, that is that the magnitude of the largest eigenvalue is equal to 1, and the magnitude of the other will be less of this one. So when we rise in this equation, we have seen we have to rise it to the power t. When t goes to infinity, the only term that remains will be the associated with the lambda largest lambda 1 that is equal to 1, and the other one will be going to 0. But just before arrive to this, that will give you the consensus value. But before to reach this consensus value, the second important lambda value will be this lambda 2. And it's clearly that lambda 2, as we raise it to the power t, when it's odd, if this value is negative, we will change between negative and positive when we change from odd to even, and so on, so on. That's why we have this oscillatory behavior on the trajectory. But if this lambda 2 is positive, it won't change of the sign. So we're going to see this smooth behavior that we see before. So the next thing that we do is to characterize these alpha 2 values, lambda 2 values, in how we change with the bias parameter. Here we have seen that in the complete network, the behavior of this, the sign of the lambda 2 value is then when we are in all group bias, we're going to have positive lambda values. And that's why the reason we've seen this smooth behavior when we have in-group bias. But this is not always the case when we are in Erdos-Renyi or Barabasi-Albert. We have seen that in the strong, when we are close to a strong biases in group over group, we have the same behavior that the complete network, but it's not clearly the behavior around the unbiased value of 0.5. But we can see that maybe it's related with the level of connectivity of the network. Now, also we have seen that the eigenvalue of 1 will give you the corresponding value of consensus. We use that to try to make a prediction of what will be the consensus value in a network with self-loop. We choose this network because it was easy for us to make analytical equations used within. What we found is that this consensus, the eigenvector associated with lambda 1 is the components are the same for the individuals of the group A. We are represented here with pi sub A, and the components corresponding to individuals of group B is represented with pi sub B, that also are the same for each one. These values can be explicitly calculated with this formula that we found, and in these formulas we have some terms that just depends on the fraction of the number of the agents of group A divided by the total number of individuals, and in the bias parameter and the constant normalization constant that is again expressed in the number as function of the fraction of the individuals in each group. So having this formula, we would like to see if it captures the final opinion consensus in the other types of network. It is complete in the complete Erdos-Renyi Abarabasi-Albert. So we made a plot of this value and comparing to the final opinion reaches with the other network, and we have found that it pretty well describes this opinion to the another networks. Analyzing the values that we reach with this formula, we have seen that when we are in the point of the no bias society, we reach to the value of the simple average. Here we are using a population that corresponds to 200 individuals of group I with initial opinion of 0, at 800 individuals of group B with initial opinion of 1. So the average will be 0.8. The another interesting thing that we have seen that when we move toward in-group bias, it is weighted more the people from the same group. We move the final opinions towards the opinion of the majority, that is opinion 1. In the other case, when we are in all-group bias, the final opinion or consensus will move towards the opinion of the minority, that is opinion of group A. Then we analyze how the consensus time change when we introduce this bias parameter. What we have found is that when the society is unbiased, is reaching the minimum time of consensus, but when we go towards in-group bias or group bias, the time increase. This was seen in all the networks, and also we can see that when we consider unequal sizes group, we have also quicker consensus when we have biased society. In order to understand this behavior, we introduced two metrics. The first one was a string-based homophily that was related with a metric, the degree weighted homophily, that was studied by Golub and Johnson, that he has found that the more homophilic network have more consensus time. But he made this degree weight homophilic using the number of links between individuals within the same group and between individuals of different groups. But the number of links in our network are keep the same, but the weights are changing. So we adapt these metrics to use the weights between individuals in the same group and the weights between links in different groups. And we have seen that we have the similar behavior that we have found the less value when the society has no biases and increases when the society gets more biases. We have looked up the relationship with the time, and we have seen that we can relate it in some way, these metrics, with the consensus time. Moreover, the second metric that we introduced was based on the self-confidence metrics that was introduced by Dean. In this case, he has found that the self-confidence when an individual is more attached to his own opinions, it delays the time to get to consensus because it remains more constant. But in our model, we are not using self loops, so there's no way to keep attached to our initial opinion. But we use the idea that when we share our opinion to our neighbors, in the next iteration, the neighbor will share our opinions in back. We capture this using the power to the square of the transition matrix W, and have found also this relationship that when we have a society without bias, the value is the lowest, and then it increases if we have a bias society. And we have made a relationship with the inverse of the logarithm of this metric to see that it's related with the time. Is a way. Clearly, there is a relation between the two metrics. So here we are exploring how if they are related. We have seen when both increase when in the two cases. But we have tested only in the case of equal size group and in only two groups. So they will needed to more investigating more to have to define if they are really correlated. Now we see how the consensus time changes as another important property of the network, that is the connectivity. For this, we increase the mean value or the mean degree value of each network, and we have seen that we increase it, we get lowest time for all values of biases. In Erdos-Rendy and Barabasi hardware, we have seen the behavior of these are pretty similar in both cases. The next thing that we tested was how the size of the network is related with the time of consensus. And here we also found that the size of the network is not so important to determine the consensus time, as it remains almost constant for different group sizes that went from 800 to 4,800. Maybe we must use very much larger networks to be able to see if there is a relationship between the network size and this consensus time. Now, and finally, we test or how if these neutral groups we cause that they mitigate these effects of the bias. And so in our networks, we add a percentage of these neutral individuals. Here in each level, there are more neutral individuals. We have seen that when we add it, we get less consensus time. So more neutral individuals, less consensus time. And also this difference is bigger when we are more farther than the no bias value. Here is shown the previous slide, but adding these neutral agents to see the importance of them. Here is seen that if we have 20% of neutral agents, we can have better times even to the complete network. So this enhance the time to reach the consensus. Finally, to conclude, I will mention some important things that we developed in this study. First, here we introduce a novel approach to the group model to study how group biases influence opinion formation and consensus. We have seen the behavior change if we are when we are strong biases, we don't reach consensus. But also, if we are not in the strong cases, we have seen that the ways to reach this consensus are different and depends on the alpha value in the relationship with the second largest eigenvalue lambda 2. We have seen that our analytical results that we use to get the final opinion in a complete network with self-loop match very well with the simulation of the other type of networks. And it also only depends on the bias metric and the relative group sizes. We have seen also the conversion time, the times to conversion is lowest when the society has no biases and increase when they show more bias. Also, we have seen the network connectivity accelerates the consensus, and the network size has no effects in the configurations that we study. Also, we have shown that we can use two alternative metrics to understand the behavior of the time in relationship with the bias that was the strain based on homophily and the feedback confidence. And also we have shown the effect of the neutral group to mitigate the time of consensus when the society is highly biased. So that's all. We want to thank you all for your attention.
Okay, thank you. Now is the time for discussion. I think we'll start with you, Juan.
Okay.